here in the plan portion as a background image. This can be screened at the plotter as well. So we're seeing that same mapping image plotted again. This time it's rotated up to fit better in the plan sheet. Once this is done, then the designer can begin the design work on the horizontal and vertical elements of the design. Here again, I should stress how very handy that is for the designer to be able to see that planimetric mapping while he's doing his horizontal design. Some of the old mainframe systems, the designer would never know a curve was transposed or a coordinates transposed until he got a printout later. Now the designer keys in his COGO, his coordinate geometry, and immediately sees it graphically represented at the screen. So the first thing a designer would do then would be to store his horizontal PIs. And here we see the graphics of the coordinates scrolling by as they're defined. 4 points of intersection. And now we'll connect those 4 PIs with COGO commands forming 2 curves and 2 tangent sections. And you'll see the very thorough reporting the system gives you. This is a nice feature of the Unix operating system. On some other systems you don't have the ability to go back. In the Unix operating system, we can scroll backwards to things that we've already seen. And I'll scroll back here to the curve definition commands and the curve reports. As you can see, they're very thorough. Length of curve, radius, length of the chord, the external, the mid-ordinate, all the coordinate values. And then we defined a chain to be the center line, the reference line. It's called a chain because you string together those 2 curves and those 2 tangents, whether you chain them together. Now this is a command for plotting the alignment. You'll see now all the automatic annotation that comes along with the plot alignment command. The designer merely has to say plot alignment, and he gets station values, ticks every 100 feet, the curves can be labeled, and in fact this curve table is a good example of the database concept in CEAL. The command to plot the curve table is simply plot curve table for curve 1. The system goes into the database, finds the geometry for that curve, and plots that to the plan sheet. Now this is something that the designer wouldn't necessarily do at this stage, but for purposes of illustration, we'll plot an existing right-of-way along the roadway. And the reason we do this now is because the system has something called schedule files, which allow us to see things plotted every time as we wish to see them. It'd be better described as classifying these objects. We classified this particular chain as right-of-way /E. And we told the system every time we see right-of-way /E plotted, we want to see it dashed with bearings and distances. Similarly, we could have said I want to see all the water main plotted in blue and solid, and gas green, and so on. So it's a powerful graphics tool that way. We'll see a few more powerful features of schedule files later on. Now we'll move down into the profile portion of the window. And here again we're going to use the digital terrain model, that 3D model of the surface. And we've asked the system to show us the profile along that horizontal chain that we defined. And it's important to note here that not only can we see the profile at the center line, but we can see that at any offset and at any horizontal location within the limits of that digital terrain model. So now the designer can examine the existing profile and key in the proposed profile by keying in stations, elevations, and lengths of curve. So we'll see those commands go by now: station, elevation, 2 vertical curves, and just like that now the curve data has been stored. And just as fast as we've stored that now, the system can go to the database with a single command, plot profile alignment, and you see we get all the information and the geometry of that proposed vertical curve plotted in the profile window. In addition, the system is very thorough with its reports. We can get a complete listing of the vertical curve geometry. I'll scroll back up so we can see this a little better. See, we have the profile report. We're given stations, finished elevations at each station. Also, we get PI elevations, stopping sight distance, passing sight distance, and K values for each vertical curve. Now that we've defined the horizontal geometry and the vertical geometry for the roadway, we'll define the roadway template to use for this particular roadway. We're going to use a little rural two-lane template. And we go now to a spreadsheet input to define that roadway template. And here you see the spreadsheet where each roadway link is defined as a change in width and a change in elevation. So you might have two 12-foot links for the roadway, 4 foot for the shoulder, and so on. Once your roadway links are defined, there's a special template for, or a special spreadsheet rather, for the cut slope section. The system will use links 9, 10, and 11 to define the cut portion, and then it will test to see how much cut it's in at that station. And you can specify what slope to use depending on what depth of cut you're in there. The same is true in fill. The system will use links 15 and 16, and then there's 3 choices for link 17, depending on the depth of fill at that station. And in addition, you can bench in cut and fill as well. So we'll exit the template menu now. So now we've defined the horizontal geometry, the vertical geometry, the roadway template, and we have this 3-dimensional model of the Earth's surface. We're now ready to generate end areas through this design. We'll tell the system which one of those parameters we're using, and we'll tell it which templates to use at which station. We can automatically super elevate around the curves. And here you see the thorough reporting again. It says it constructs end areas at each station. We've also told the system our right-of-way limits are 65 feet on each side of the center line. Don't exceed that limit. In fact, if you do, pull those back slopes in at those points. And we see the messages we're getting. Warning, left side right-of-way limit exceeded, shifting catch point to 65 feet, and the slope is given. Now, just that fast, we've generated volumes and end areas throughout this design. And we can see those volumes immediately. Here again is a very thorough report with a mass haul, cumulative and incremental volumes. This can all be scaled by expansion and shrinkage factors. And also as a byproduct of those end areas, we can see a mass haul diagram as a byproduct of those end areas. CEAL will use the mass haul ordinate to plot the mass haul diagram. This will be very useful for balancing the cut and fill on a project. You can see how fast it would be to change your vertical profile slightly, rerun the design, and optimize your earthwork. Another power can be extracted from the end area models is the slope stake limits. Here we see again the horizontal geometry plotted and the existing right-of-way plotted. And now in white you're seeing the envelope required to build that new roadway. Those are the slope intercept points constructed from that end area model. In addition, the designer has the ability to offset those limits for a clear zone as well.